Hello and welcome to Calculus 1. So Calculus, which was the study of change, as we talked about it last class, contains three parts. So Calculus will have limits, which is going to be your chapter 2, derivatives, which are chapters 3 and 4, and then integration, chapters 5, 6, 7, a little bit excessive, I know, 7 and 8, and then chapter 9 is the mixture of all three. It's a little chapter on differential equations, but you are going to have a whole course on that eventually, maybe. And then the two chapters that use limits as application. And then Calc 3 will be Calc 1 from scratch. Limits are going to provide base to study everything else. You know how you learned at one point in life addition, and you constantly keep adding, right? 3 plus 7 is 10, hopefully. Limits is in that category, right? Limits, section on limits, chapters on limits. So limits are in that category where you will use them to define derivatives, you will use them to define integration, do the Riemann sums. You will use limits to deal with sequences and series in Calculus 2. So limits are something that will never, ever, ever go, well, nothing here goes away because 100% of what you learn in Calc 1 will be used later on. We are not going to have a section that it's not used at all later. They're either used heavily or they're modified and used again, especially in Calc 3. So Calc 1 is the base for Calc 2, Calc 3, and obviously differential equations coming on later. The first part is on limits. And I like to give you the street definition first, because the precise definition of the limit is all the way at the end of the chapter. I don't know why, but such is the way of our book, right? So what we have is first the idea and the notion of limit, and the simplest way to understand what the limit is just the way I call it, fancy way to compute y value of the function. And I'm actually going to write that down. Fancy way to compute y value of the function. So this is something that I call the street definition of the limit. It is not a formal, obviously, mathematical definition. This is just for us to understand down to the simplest possible explanation of what the limit is. So, if you have that f of x is given as 2x plus 3, f of 5 is 13, and the limit of 2x plus 3 as x goes to 5 is also 13. So this is you seeing the limit notation possibly for the first time, and it simply reads limit of, and then you have a function in here, is, which is equals, and then a value that you get on the other end. So now you have a way on the left, which is our pre-calc way, and this over here is, well, that's calc. There you go. We got the same 13. Are these answers always going to be the same? No. They are not always going to be the same. It will depend on the function and the value you need to compute, or what type of answers you are going to get. But before we get into those cases and all of the other things, let's understand why am I calling this a fancy way to compute the limit rather than just say computes the y value and move along. Your precalculus is what computes y values and you move along. So this stuff here that you are used, or algebra 2, whatever you learn this, that is just computing the value and move on with your life. Limits provide much more. And obviously, we would not have a different procedure for the same thing if it was exactly the same thing. So, what's so interesting about limits? Let's take a look at a very simple idea. Over here, a graph. Y equals x squared. And say you are looking at value 3, which is to produce 9, because you know that if the function f of x is x squared, from precalculus f of 3 is 3 squared, which is 9. So what you see on the screen is your good old life from precalculus. You have your x-axis, you have your y-axis, and so on. Now, what's this deal with the limit? You see, the limit, as x approaches 3 of x squared, is also going to give us 9. And I need to show the way it gets to 9. Limits do not compute at the value. I'm going to write that in blood. Limits do not compute at the x value. You are not computing this 9 by plugging in 3 and saying 3 squared is 9. You go, huh? Yeah. What we use is what we call a one-sided approach. That's math talks. I like to call this method Romeo and Juliet approach. Do you know who Romeo and Juliet are? Is everyone familiar with them? If you haven't read the book or seen the movie or something, they die at the end because they're stupid teenagers, okay? Anyway. So this is what happens with Romeo and Juliet approach for limits. Juliet, red for the girls, right? So here we go. We are approaching 3. That means you are walking on the x-axis where your x value is rising up to number 3. Now, this motion of you walking on the, or Juliet, walking on the x-axis translates to walking up the function which goes up the y-axis. Now you can actually test certain values. Let's say she's here, that will bounce there. She moves forward, bounces there. So as you can see, as she walks closer and closer to x, her y values are getting closer and closer to 9. Do we all see that visual? That's Juliet, red. Romeo, on the other side, obviously blue for the boys, it's going to go, I'm all about stereotypes, by the way. So, yeah. So, we have a Romeo approaching from the right. As his x values decrease, he's walking down the line, walking down the y value, and they are actually going to meet at y equals 9. Limits do not compute at the value. They compute everywhere else except at 3. Juliet took on all x values before 3. And Romeo took on all of the x values after 3. And they computed the y values, infinitely many y values, before and after 3. Neither of them computed at 3. So this is the difference between the precalculus computing the value of the function and the limit computing the value of the function. Limit is going to look at the trend. Okay, the values are rising into y, or the values are, the values are rising towards 9, the values are dropping towards 9, so the answer meets at 9, therefore that has to be an answer. So it's inferring the answer. It's not calculating 9, it is observing all of the values that are going towards 9. Now that is very easily explained and seen if you take a look in the chart of the values. You provide x and y, right? X and y. So here are the three. These are going to be x's. These are going to be y's, right? And I'm going to put some divisions here where we are going to stuff the Juliet values and Romeo values, and we are going to see that the y value screams go to 9. So on the left side, which is Juliet, which is red, she is going to approach 3 with x values 2.9. So she's like 10 cents away from 3. Then 2.99. Now she's 1 cent away, so she's closer, right? And then 2.999. This is like buying the gas at the gas station where they have, it's $2.41, and then they have 9 over 10. When I moved to US, it took me 3 months to find someone who knew what that was. Because, as a geek, you drive around, you see a fraction in a price. I mean, you go like, well, what is it? Do I buy 9/10 of a gallon or a liter or something for, right? I was trying to figure it out. And then someone said, oh, no, that's 9/10 of a cent. And I'm thinking, the lowest denomination of money is 1 cent. I mean, how do you give me change? I want change. Oh no, computer rounds it up. Why do you bother printing it then? What the hell? Anyway, so there you go. See, Juliet is first 10 cents away, then she's 1 cent away, and then she's 1/10 of a cent away, right from 3. And then you can use your abacus to figure out what these values are when you square them. So we'll start with 2.9 squared, which would give you 8.41. Then 2.99 squared, which will give you 8.9401. And finally, 2.999 squared, which will give you 8.994. What is the trend that we see in the y values for red numbers? The trend is going where? Going towards 9, right? So these numbers are rising into a 9. All right, let's see what's Romeo doing on the other end. Romeo is going to be 3.1, which is 10 cents away from 3. Then 3.01, which is 1 cent away from 3. And then finally 3.001, which is 1/10 of a cent away from 3. And now you have 3.1, which is all the way to the right. So 3.1 squared is 9.61. Then 3.01 squared will give you 9.06. And then 3.001 squared will give you 9.006. What is the trend here? Goes again towards 9. We see that the red numbers are rising to go into 9, and the blue numbers are getting smaller, diminishing to get into 9. Well, If it walks like a duck and quacks like a duck, it's a 9, right? It's a duck, yes. So that's it. We are done with limits. There is I know, right? So we're going home. Time to go, yes. So we are done with limits, and believe it or not, the rest of the chapter are just fancy thing about limits. This is where the limit begins and where the limit ends. You can literally bypass everything else you learn if you are willing to spend time punching the numbers in the calculator to come up with these values. Now, obviously, the functions get trickier, they get longer, they can, right? So we can do a lot of what I would describe as interesting things. You might have a different definition. But entire chapter 2 is this. You have a function and you want to take the limit as the limit goes to 3 or negative half or let's say negative infinity. You want to know what the y value is doing as the x value goes to particular point. Last class I mentioned that calculus is a study of change, evolving and motion and so on. You have the motion encoded in the arrow. X goes to 3. See, that's the reason why you have this very important sentence. X is not 3. X goes to 3. And that is a different concept, right? You can test that. There is a very famous example to understand special theory of relativity. If you are not familiar with that part of physics, it goes like this. It's actually a very cheap idea because time is relative, and you actually can do the experiment yourself. Time is relative in the sense that it flows differently from different frame of reference. The best example, obviously, is which side of the bathroom door you are, right? Which side you're on when you really have to go, right? You see, time is relevant, right? Sometimes you might not worry about 30 seconds, but in that situation, probably you will, right? So thinking about that example, for instance, right? You see that it's not the same of, going to the bathroom, which is 30 seconds going, or being there. It's completely two different concepts. So that's the difference between the precalculus and calculus in this case. Calculus computes not as a value, but as a process of getting somewhere, which is that part where this is motion, it's evolving, it's changing, right? So x is going to 3. You see, x is going there. So there is 2.9, then there is 2.91, and 2.92, and 2.93, and you can make stops at each one of these values to compute. And there are actually infinitely many numbers to compute in between any numbers you would put down, right? Then you wonder how you ever get anywhere when that's the case. But we'll get there as well in Calc 2, unfortunately, right? So the idea is to understand that the limit is the process of going somewhere, and the number you get at the end is that final destination, the place where you get to after the process of going, right? So the difference between precalculus and calculus. Here's another idea to understand the difference. Let's say over here, this over here, no, don't do that. Deselect, there we go. So over here, we're going to have a cross section of a river, and now we're going to have some bridge stretching across, except this bridge is going to have a section missing. this comes in handy. You can only pay like half of, like you can charge half of the bridge, right? Fair, because there's a piece missing. That piece is here. It fell off, and it's in the river below. All right. This is why I never became civil engineer. I was mainly concerned with what happens when this stuff breaks. So, you know, the rest of the bridge is there, right? So there we go. All right, so that's a bridge, and there's a little section missing, right? So this is what precalculus gets to do. Precalculus goes and say, what's happening, 1,000 feet into the bridge? There's a hole. And that's it. That's all you can do with precalculus. Calculus is the one that actually allows you to fix it. Because calculus allows you to, well, in this case, Juliet, I don't think she would be very useful fixing the bridge, because they didn't have bridges at that time, but that's okay. I mean, these types of bridges. And then Romeo, also not useful. Coming back from this side, going towards. You see, we have two different ways to approach the problem using calculus and get to the part where you can fix the bridge, right? The precalculus does this. It's broken and just walks away. That's the precalc. Talk about the attitude, right? Where the calculus says, well, we can approach from two sides, and then we can actually, hopefully, maybe fix it, Do they all end up at the same location eventually? The answer is yes. So precalculus just detects that there is an issue, where the other two actually approach the position and get to the same value, they get to the same conclusion. So two different ways of approach. Now, the red one, so now we're talking about one-sided limits. And here again, in parentheses, I'm just going to write real quick. Let's use orange. I can do it here. One-sided limits always exist. Because as soon as we are done with this little section, we are going to see situations when limits do not exist. Right? So we'll have all different combinations. So one-sided limits always exist. Maybe I should scream that one. Let me scream that one. There we go. So we have two one-sided limits, one for Juliet and one for Romeo. So Juliet one-sided limit is the approach from the left. And that was Juliet, which was the limit of f of x. And then we write here x approaches a, and you put the minus. This minus is in the same spot like if you are to write a squared, and instead of squared you put a minus sign. So it's a superscript, right? Superscript. Subscripts are down, superscripts are up, right? So it's like a square, but it's instead of square you put minus sign. So that's the approach from the left. You are using the notation x approaches a minus. Now the blue side is the Romeo, so approach from the right, and that is going to be limit of f of x where x approaches a plus, and that would be from the right. So now we have these two, what we call one-sided limits. So what we discovered earlier in our example when we considered f of x equals x squared, we said that the limit x approaches 3 of x squared is 9. Well, that had in that chart, right, the left approach, right, and the graph, left and right approach. So we can actually write limit of x squared as x approaches 3 minus. That's a Juliet, and she gets 9. And the Romeo, on the other side, limit x approaches 3 plus for x squared, and he gets 9 as well. And then we said, if it walks like a duck and quacks like a duck, it's a duck, right? So from both approach, values are 9. So 9 equals 9, and the overall limit is 9. You see, overall limit approaches from both sides simultaneously, right? At the same time, where the left and right approaches, which is what I color code red and blue, those approach independently of each other one at a time. And when they are equal, then the overall limit is the value. And if they are different, overall limit does not exist. So here is one of the largest theorems of chapter 2. And this is the one that actually is used to solve problems. Theorem says like this: if limit of f of x as x approaches a minus is the same as limit of f of x as x approaches a plus is equal to some number L, then the overall limit x approaches a of f of x is L. Otherwise, limit does not exist. So at this point, I get to welcome you to calculus. In calculus, theorems are what you use to solve problems. What you see here is like a step-by-step instruction on how to do a problem. If the left and the right approach give the same value, that value becomes the limit of the problem, which is the y value. We said a fancy way, right? If the left and right approach produce different answers, which is the otherwise, right? Because you see there is equal, otherwise mean not equal. So if the left and right, if the red and blue produce different values, in that case, limit does not exist. So now let's take a look at the example where limit does not exist. We are going to take a look at something that is called a step function. Now, these step functions are used in many applications. One of the most famous ones are taxes. Tax brackets would be a step function. And we can actually use that as an example because tax brackets are always available to us, right? It's public knowledge. So let's take a look at tax brackets 2019, for instance, the ones that we will be filing in next year, right, by April 15th. So here are the tax brackets, and what I see here is, 9,700, call that 10K, okay? So 10%, you pay 10% up to 10K. So x-axis is money, and y is the percent. Was there a sneeze or something? Amazing. You're like a ninja. All right. If you are earning 9,701 to, so I'm just going to say 10K to 40K, your taxes are 12%. So we'll put 12% supposed to be here. So I'm just going to move this. So here's the 12% and here's the 10%. So from 10K to 20, I need this to go wee. So that's 20K, that's 30K, that's 40K. So if you're making up to 40K, which is actually not 40K, 20K, holy nightmare. 20K is the cutoff. So 10%, no, I looked at the other one, which is the main, I was right with the 40K. 12% is up to 40K. I looked with married, this is single. And then from 12%, it jumps to 22%, which is here, if you are making over 22%, if you are making between 40K and 85K. So that's going to be 50, 60, 70, 80, 85K. And that's there is also Bill Gates category here, but let's end at 85K, because I don't think anyone in the room would be making over 85. I mean, maybe you do, I don't know, but let's just end it there. There are more than this. So what you see here is called a step function. So if you make in any money in one of these brackets here, you will be taxed at that percent. So that part of your earnings will go to the government and the rest stays with you. So if you're making less than 10K a year, 10% goes to government, 90% stays in your pocket. If you're making, let's say, 50K a year, then 22% goes to government, 78% stays in your pocket. Now, these particular functions have values everywhere, but at the places where they make this jump, there is no limit. So if I am to calculate, and we'll call this this function tax function. So let's call it T of x, right? X is in dollars on x-axis. So T of x, tax function. T of x, tax function. So here we go. If I calculate the limit, which is just the y value, which is just the percent you have to pay. If I calculate the limit as x, which is the amount of money you make a year, x goes to 5K of the tax function, the answer is 10%. Because the answer to that is 10%. If you're making 5K, 5K is in between 0 and 10K, so you're paying 10% tax. If you are looking for the limit x goes to, let's say, 38K in terms of money of the tax function, then you are paying 12% tax, because 38K is less than 40K, which is the cutoff point. For, it's not exactly 40K, but 39,475 is the cutoff. So, right? So these are actually values where you are approaching, and you see that if you approach from the left, you approach from the right, you always get the same y value, because these functions are all flat. That's why they call step function. They look like stairs, like steps, stairs. So step function, right? That's why it's called that way. 38k, again, it's a value right there for 38k. And you go from the left, you go from the right, right? But now, what is the limit as x approaches 10k of the tax function? Well, immediately you see that that's where the jump is. And the answer would be no limit. And the reason is, here we go with Juliet. Now we are using the theorem I just stated. We take a look at the x approaches 10k from the left. So Juliet would be walking on this lower tax bracket going towards 10k, and she would report that the tax bracket is 10%. Right? Romeo, on the other hand, the blue one, approaches x 10k plus from the right. He's walking on the higher step going towards 10k for this tax function, and he's reporting 12% on his side. And they're not equal. Therefore, because of this issue here, we have to say limit does not exist because these two didn't agree. Right? Didn't agree, there's an argument, the death, and that's it, done. So that's the idea of limits. You either have both values from left and right agree to the same number, like we had earlier, agree at 9, and the limit, overall limit is 9, or they end up being different values, and if they are different values, then the limit does not exist, and we just go on, we just write does not exist, and we move on with our life. The last situation that we need to discuss is the situation where the function value exists and the limit exists, but they are not the same value. And that is the bridge situation we talked about before. You see this? I'm going to draw a mathematical function for this. Romeo and Juliet agree because the bridge is level, right? The bridge is level, and both Romeo and Juliet are going to get the same y value, so limit exists. And even though the segment of the bridge is not there, the limit is that value, which is why you can fix it. The function of value, which is the segment of the bridge, is in the water. So it's a different number. And that, where later, in next week, that idea will define continuity. You see, that bridge is not fine for us to drive over, right? Because there is a section missing. So the requirement will be function value exists, limit exists, and they are the same, right? So that's going to be later on for continuity. We'll come back to that. Right now, we just need to understand from math perspective the bridge situation. So here I have a function, right? You can call this a wholly function because there is a hole in it. And you will dislocate this value somewhere. So now, all of this is happening at x equals a. And this is my function f of x. So if we are to do the limit for this abstract function, we have no problems. What is the limit as x approaches a of f of x? Well, let's ask Romeo and Juliet. So Juliet approaches from the left, so a minus. of f of x, and she is going to get this value L, because she's approaching from the left, walking, in this case, up the function, up towards L. Romeo, on the other side, goes from the right, and he is going to go also into L. And because both of them agreed, the overall limit is L. So yes, the black writing came first because that's the question, but the answer, which is orange L, is a consequence of the blue and red L's. So technically, you working out the problem is doing the red and blue and making conclusion. Because they're the same, you get the orange L as the answer for the limit. Now, Precalculus says that f of a is here. So f of a exists, but you can see that f of a and L in this case are not the same. So that's important. So in this case, meaning this problem, L is not the same as f of a, because the point is dislocated. So now you see advantage of calculus and limit calculations, because clearly the limit, which is there, the value is not there, but we are still able to detect it, which is why if the section of the bridge is missing, you can fix it, because you are able to approach it and fix it, right? Work on it. Precalculus doesn't give you any idea what's happening with the rest of the function, because it deals with points one at a time. So those are the deficiencies of precalculus calculations, which is why calculus is more powerful, right? Now, there are certain situations when you want the precalculus answer, so of course you're going to use it, but I hope that you understand that the concept of the limit to compute a value is far stronger, right, than the concept of precalculus. Because precalculus deals with the point at the time, and if the point is missing, oh well, such is life, right? Where this guy actually computes it. The last example is going to involve infinities, because you don't get a good calculus lecture or section without involving infinity, right? You have to. So here is a good old function that you need to have memorized and know it, and you'll be sick of it. F of x equals 1 over x. Well, this function is all over the place, and the sooner you memorize its graph, the better your life will be. And here are the x and a y. It has these two parts like this. That's your 1 over x function. And now you might be interested in, a couple of different limits there. Observe that limits are actually the same as the value of function for all values except which one? 0. 0 is the only problem point on the entire graph. That's the one that makes this explode. No, I'm serious. Have you ever shorted the outlet? What happens? Explodes. What is there in the equation? 0 in the denominator. So when I say explodes, I'm not joking. I'm serious. All right? 0 in denominator creates explosions. Sometimes you buy a cell phone or a laptop and the battery goes. It's the same thing. All right. So, yeah, the engineers missed division by 0 somewhere, and that's what you get, right? So hopefully you'll be the better batch, right, of engineers. So observe what's happening as Romeo and Juliet do their approach. Juliet will approach 0 from the left, which is limit x approaches 0 minus for 1 over x. And as you can see, she will just slide down this one where? To negative infinity. Very good. What is happening with Romeo? Approaches from the right as the limit x approaches 0 plus of 1 over x goes where? Positive infinity. So what is the conclusion when you see them like this not being the same?
There's no limit.
There is no limit. At 0, all others exist, right? Limited 1 is 1. Limited 2 is 1/2. Everything else exists apart from at 0. So limit x approaches 0 of 1 over x does not exist. So this is the first part of the example. Here comes the second part of this example. We are going to put the g of x to be 1 over x squared. Now that is also a useful graph to remember. It's very similar. This square is going to bump the negative line up. So it looks like this. All right, Juliet, what's up? X approaches 0 minus 1 over x squared is what? As she approaches 0, where does the y value go? Positive infinity, plus infinity. Romeo, 1 over x squared as x approaches 0 plus from the right side. Where is he going? Positive infinity. So what's happening now, using our theorem, they both agree with each other. So the limit is positive infinity. So they will live forever in a story. Right? There you go. See? At the end, we turn the tragedy into something positive. Cool, huh? And then you tell me Shakespeare was not a mathematician. Look at that. Amazing. That's it. I don't really have any kind of closing for these classes here.